you can sketch a graph easily enough, you should. Now that we've just finished up with increasing, decreasing, and points of inflection, we really, truly now have everything that we will have, every tool to help us figure out what even the most complicated graphs look like. So we're going to go through some of these. A lot of this is older stuff, but then obviously some of the newer stuff that can help us determine what a graph looks like, the increasing, decreasing, and points of inflection stuff. So the first one is just a rational graph, and when we talk about domain, I think asymptotes is really one of the keys there. That applies to horizontal and vertical, so I'm going to put asymptotes in parentheses. So if I rewrite this first function just so it's factored out and a little bit clearer. Where do I have asymptotes? Give me at least one Lizzie. Nope, that's right. Yeah. X equals -2. It's going to be a vertical asymptote. So I do -1, -2. Anything else? +2 here. Good. Okay. How about horizontal asymptotes? Y equals 2. In that case, I might want to think of the function as 2x squared minus 18 over x squared minus 4, because then it's same over same. So y equals 2 would be the only horizontal asymptote. Okay, raise your hand if you can tell me, I think that covers asymptotes. Any other features of this graph? Anything? Any point, anything? Any end behavior? Worst case scenario, you could just start with a table of values. But that would be a worst case scenario. I'm probably not going to be doing a table of values ever, because we have a whole list of features to run through. And right now, if we just go through the checklist, you're at intercepts. Matt, how do you find intercepts? Make what equal to 0? Say it again. Well, we already made the bottom 0. That did not give us intercepts. That gave us asymptotes. Right, okay, so if we set the equation equal to 0, which I can do here, technically we're setting the y equal to 0. So what intercept are we looking for if we just set y equal to 0? X, correct. If you set y equal to 0, you're looking for the x-intercept. Now, the only way the fraction is going to equal 0 is if the what equals 0? Numerator. So what are the two x-intercepts that would make our numerator equal 0? Yeah, x-intercepts at x equals 3 and -3. Symmetry will come back to it. That's probably going to be, well, I don't know if it has to be. It depends on your preference. But for me, that's kind of one of my last resorts. What about the other intercept? We have our x-intercept. How do you find a y-intercept? Plug 0 in for x. So y equals 2 times 0 squared minus 9 over 0 squared minus 4. It's going to give us -18 over -4. Which is a y-intercept of 4.5. Okay? So now we have a good basis here, especially because we've seen enough rational graphs in our day to know that when you come up with these asymptotes, you're kind of creating new, I'll use the word quadrants even though there are more than 4 of them, but you're creating new sections for these little corners to have a curved graph kind of nestled into. But we should also know that as we approach asymptotes, what happens? As you approach a vertical asymptote, where does your graph always approach? Correct, infinity or negative infinity. So if I wanted to approach this -2 from the left, I would plug in something like -2.1, correct? So if I were to plug in something like -2.1, I'm not going to get an actual value, but I'm really on the lookout for, is this going to go towards a negative infinity or a positive infinity? Because as I get closer to a vertical asymptote, I'm either going to shoot up towards positive infinity or I'm going to shoot down towards negative infinity. What's your guess just by looking at the graph? Right, and why are you saying negative, Brian? Right, because even though you can cross horizontal asymptotes, usually they're kind of guiding your end behavior. So as I go out this way, it's probably going to guide my end behavior as I approach negative infinity, which would only make sense that this would then come down towards negative infinity. But let's still check it. When you plug in -2.1, is your numerator positive or negative? Negative, because -2.1 is kind of somewhere around 4. 4 minus 9 is a negative. Over. And what's going to happen to your denominator? Right, so, but barely positive. A very small positive. So it's a negative number divided by a very small positive, which does tell us negative infinity. So as we're approaching -2 from the left, we are going towards negative infinity, which kind of matches up with our function headed towards that asymptote as we go towards negative infinity. So what happens, and we'll focus on this vertical asymptote, what have we talked about regarding behavior on either side of a vertical asymptote? Sometimes, but that's the idea I'm looking at. Are they opposite of each other? When are they opposite of each other, meaning this one goes towards negative infinity and the other one would come from positive infinity, versus when do they both go towards negative infinity? Noah? It's not the numerator that would be squared, it's the degree of that asymptote factor. So the factor that created that -2 asymptote is right here. Because that has a factor, or has a degree of 1, it's going to be opposite behavior on either side. So you don't need to really waste your time plugging in a -1.9, although you can if you're in doubt. If you plugged in a -1.9, you're going to get a negative over a negative, which would indicate positive infinity coming from the right. But you shouldn't have to do that if you know that degree rule for an asymptote. So if this x plus 2 was ever squared, that would mean we've got the same behavior on both sides of the asymptote. But because it's only to the first power, that is approaching positive infinity, which also should make sense because we have a point up there that we need to go through. Yes? So that should make sense. And at some point, we have to hit that. If you want a little extra confirmation, you could always plug in a -1 and see that that point is up here somewhere. But then what's going to happen? Is this going to wiggle down and go towards negative infinity, or is it going to go back up towards positive infinity? And we could kind of use the same logic that we just did over here on the right-hand side of the graph by checking, like plugging in 2.1. Okay, again, as we approach a vertical asymptote, it's got to shoot up towards infinity or negative infinity. So if I plug in a positive 2.1, I'm going to get a negative over a positive again. So that's going to also be negative infinity as I approach 2 from the right, which I'm assuming most people would have hopefully guessed anyway, because, again, our end behavior has to approach that horizontal asymptote. What is the degree of the factor that created this asymptote? 1. So it's to the first power. So if it goes towards negative infinity on this side, it's probably going towards positive infinity on that side. It's odd again. It keeps flipping back and forth. So it would be opposite behavior again. So that's a sketch of that graph. Some of the stuff we did not get to, but we could have. The symmetry idea I do want to talk about. This is an Algebra 2 topic, but to find out about even or odd functions. Does anybody remember what you do for even odd function tests? You plug in negative x. So if you plug in negative x, if you get back the original, it's even. If you get back the exact opposite of the original, it's odd. Even means it's symmetrical to what? Yep, symmetrical to y-axis. And odd means it's symmetrical to origin. Hopefully my output too, kids. Yep. And because it's even, then you would know that you have the symmetry, which could have saved us some of these steps. Because this one is an even function. If I plug in negative x and see what happens, 2 times a negative x squared minus 9 over negative x squared minus 4. When you're squaring these negative x's, they're turning right back into the x squareds that they originally were. And so this function is an exact match to the original once I clean that up. And because it's an exact match to the original, it's even, and we know that this graph should have been symmetrical to the y-axis, which, of course, it was and made sense. We didn't, use that idea to draw the graph, but we certainly could have. It might just say sketch it. Just open response, sketch it. If it did, I could ask you specifically, like, is this one even or odd, or I could give you a checklist, or I could just, whatever ways work for you. And that's going to change depending on the problem. I would say, what is the, what are your go-tos? Certainly with rational graphs, your asymptotes are going to be a huge guide for you. But that's going to change when we're not dealing with a rational graph anymore. The other 2 pieces that we didn't get to but could have been helpful were the first derivative and second derivative pieces of information. So if you had found the first derivative and set it equal to 0 and undefined, you would have gotten critical points at -2, 2, and 0. And I'm just showing this without doing the first derivative and so on. I'm telling you that you would have gotten critical points where the derivative was 0 or undefined here. So if you tested the derivative at -3, you would have gotten a negative, which is an indicator that your graph is decreasing. Yes? Then if you tested the derivative at -1, you also would have gotten that the graph is decreasing, which would tell you that -2 is not a relative extrema, which it's not, right? It's just an asymptote, and because it was an asymptote, there was a potential for it to change from increasing to decreasing, but obviously you can see this is decreasing, going down. This is also decreasing. At 0 and beyond, however, between 0 and 2, you would have evaluated the first derivative and you would have gotten a positive, which would have indicated that it did increase. And so because of that change from negative to positive, increasing and decreasing, and the fact that 0 is defined on your function, that would have come up as a relative minimum. And then from beyond 2 to infinity, it would have been increasing again, which would have ruled out 2 as a relative max or min. And then obviously, again, because 2 is undefined completely, of course it wasn't going to be a relative max or min. And then your second derivative would create critical points at just -2 and 2. Prior to -2, you would have gotten what? Just looking at the graph now that we know what it looks like. Is this concave up or concave down? Down, so you would have gotten a negative. At 0, is this concave up or concave down? Up, so you would have gotten a positive. And beyond 2, is this concave up or down? Down. But again, you're not always going to need to do all of these things. In fact, it's going to be rare that you ever have to do every single one of those things up there, but nonetheless, they should all still work. It's just do as much as you need to come up with the graph. Okie doke? All right. On this next one, kind of one of those that Anthony asked about on your homework with the square root. So if we want to start with asymptotes again, because it is rational, where are the vertical asymptotes? There are not any, correct. Your denominator will never equal 0. Where are your horizontal asymptotes? And -1. So at 1, you have 1, because it's same over same, because the square root of x squared is just x. So it would be same over same as far as the degree is concerned, and 1 and -1 because of that square root wrinkle. So towards one of the infinities, it's going to approach the 1. Towards the other infinity, it's going to approach the -1. And you could sort of already figure that out. If you plugged in a positive 1,000, like a positive infinity type number, is that going to be a positive 1 or a -1? If I plug in positive 100, that's going to be a positive over a positive. Positive over a positive is positive 1. So it's going to approach positive 1 as we go towards positive infinity. The problem is, I don't know if it's going to approach it from the upper side or from the lower side. You know what I mean? There's a couple things that could happen here. It could go above the graph and then kind of come back down, or it might just go right up to the graph. I don't really know yet. But I do know it's going to be around positive 1 as we go towards positive infinity, and then if you plug in a negative huge number, you're going to get a negative over a positive, which is going to indicate that's going towards -1. Good? But we don't really know enough yet. So those are our asymptotes. How about our intercepts? Aaron, how do I find my intercepts? Set what equal to 0? Well, technically I'm setting y equal to 0. To find my x-intercept, in which case the x-intercept would be 0, right? This is my x-intercept work. To find my y-intercept, I set x equal to 0. That's going to be 0 over root 2, which is going to be 0. Which I already have graphed, so it's the same point as my x-intercept. And then I can check symmetry. If I plug in -x, I'm going to get -x over the square root of -x squared plus 2. And when I clean that up, it's going to be negative x over the square root of x squared plus 2. How does that compare to my original? Is it exactly the same? Is it the exact opposite? Yes, it is. The opposite just means it's been negated. And I've negated it. I think from Algebra 2, you guys are used to really only looking at polynomials. In which case, because you're negating the entire polynomial, every single sign is switched. That's not the case with non-polynomials. This is a perfect negation of the original. So this should be symmetrical to the origin. Still though, I don't know if this is, I've got two kind of graphs floating around in my head. I've seen stuff that looks like this. That would be symmetrical to the origin still. Versus I've seen stuff that looks like just like this. And that's also symmetrical to the origin. So what does this one have that this one would not have? Relative mins and maxes. So when I've sort of run out of everything up here, and I've looked through all that stuff, I'm left to focusing on how my derivatives can help me. So if I find my first derivative and try to search for relative mins and maxes, if I don't have any, it's probably going to be that the second graph that I had drawn. So before I find the derivative, I would probably rewrite this as that. Bring my x squared plus 2 up to the numerator, to the negative power. So for my derivative, I need a product rule. So first times the derivative of the second. And that product rule just there requires the chain. Plus my second times the derivative of my first, which is just 1. So how should we clean this up? What do you see first, Sierra? Okay, so this 2 and this 2 are going to cancel, right? So that would be a negative 1 times an x times an x. So that's negative x squared. And then x squared plus 2 to the negative 3 halves. Plus x squared plus 2 to the negative 1 half. Thoughts here? Pooch, what do you think over there? What would you do to this? Eventually I need to set this equal to 0 or undefined, but before I get there, so just go right into the fraction. I'm going to show you why that's not a good idea. And then I'm going to let the other two people speak up here. If I were to do that, it would be x squared plus 2 cubed, and then the square root of that, plus 1 over the square root of x squared plus 2. Which, I mean, maybe I could still survive. If I set that equal to 0, and undefined, it's actually not ever going to be undefined, because my denominator will never be 0. I could subtract this over and attempt cross-multiplying. It may work itself out. I would have to do it, but I don't want to take too much time away from what Catherine and Jane are going to tell me. Catherine? Correct. So these are the same base. So we did this earlier in the year as a skill. It came up recently, but not a ton. But we would factor out the x squared plus 2 to the lesser of the two powers. Which one's the smaller number? Negative 3/2. So I'm going to factor out x squared plus 2 to the negative 3/2. And what's left of this first term is just negative x squared. When I take this second term, and I'm going to show it so it's a little bit more clear, I'm dividing out x squared plus 2 to the negative 3/2 power. When you divide common bases, what do you do with the exponents? Subtract. So negative 1/2 minus negative 3/2 is the same thing as negative 1/2 plus 3/2, which is 2/2, and 2/2 is 1. So it's just plus x squared plus 2 to the first power, which obviously cleans up well, because the negative x squared and the positive x squared now cancel. Now, Pooch, I think I would go to the denominator scenario. So this is going to be 2 as my numerator, and then the x squared plus 2 cubed, but the square root of it is going to move to the denominator. And there is the first derivative. So when does that equal 0? Never. When is it undefined? Never. So when do I have relative maxes and mins? Never. So that answers my question that this should not go above the asymptote and then turn around. It should just straightforwardly kind of go up and approach that 1 asymptote as we go towards infinity, and the negative 1 asymptote as I go towards negative infinity. Follow? If you're not confident and you want added, added confidence, we also could look at the second derivative, which will not be nearly as ugly as the first derivative, because if we left off with that as the first derivative, our second derivative is just a power rule. So when I bring the negative 3/2 out in front times 2, what's that give me? Negative 3. And then negative 3/2 gets dropped to negative 5/2 times the derivative of what's inside, which would be 2x. So the second derivative is just negative 6x over the square root of x squared plus 2 to the 5th power. When does that equal 0? At 0. When is it undefined? Never. So if you test a 1, you're going to get a negative over a positive, which is a negative, which means it should be concave down. And sure enough, if you look at your graph, from 0 and beyond, it's concave down. And then if you plug in a negative 1, you're going to get a positive over a positive, and that's concave up. And if you look at your graph, it is concave up. Again, you didn't need to do that second derivative thing. We kind of had it prior to that. The other thing you could do is just check points. If you just want to plug in 1, plug in 2, it would probably be more efficient here, because if I plug in 1, my y-coordinate is going to be 1 over what? If I plug in a 1, what's the denominator going to be? Root 3. If I plug in a 2, I'm going to get 2 over root 6. If I plug in 3, I'm going to get 3 over root 11. So is this number ever going to be greater than 1? No, and for that reason, you would know it never went above 1 and then evened out. It just stayed right below it the whole time. So you could also get that without doing the derivative stuff. Good? Okay. Flip over to the back. I want to change this question, actually. I don't like that one because it's not factorable. I mean, it is, but not by grouping. So, graphing something that looks like this. First of all, it's a polynomial. So you should already know what the end behavior looks like for an odd-degreed polynomial with a positive coefficient. You should know it starts low, somehow it ends high. Right? Once you're there, you should, again, find your intercepts. What's your y-intercept? 3. What's your x-intercept? You'd have to set it equal to 0, right? Does anybody know your x-intercepts here? Because this is not factorable, right? The next thing I would probably look for, there's no asymptotes, would be relative max and mins. So if I were to find the first derivative, when does this equal 0? Now I can factor it. I can pull out a 3x, and I have a relative something at x equals 0 and x equals 2, and I'm about to find out what. At negative 1, is my derivative positive or negative? If I plug in a negative 1. The negative times a negative, positive. If I plug in a 1 to my derivative, I get a positive times a negative, which is a negative. So what's happening at 0? A relative max. It was increasing into it and decreasing out of it. And I already have a point there, so I can kind of get that framework there. At beyond 2, if I plug in a 3, it's a positive times a positive. So right at 2, I have a relative minimum, right? But 2 what? I would need to plug 2 back in and figure out the y-coordinate, so I have my relative minimum. 2 cubed is 8, minus 3 times 4, so 8 minus 12 is negative 4. Negative 4 plus 3 is negative 1. So at 2, negative 1, I have a relative minimum. So my zeros weren't going to be nice, but then it's also going to flip back around because we know end behavior. And we don't know our zeros, but we knew our relative mins and maxes, so that could guide us enough to come up with the sketch of the graph. And that is all of that. You don't have to do it all for everything, though. That's the thing. There's so much that you have to know, and that kind of brings it all together.